Scientific notation gives us another set of names that are sometimes useful when we're talking about very large and very small numbers. So let's look at this number, 32 million. It's a pretty big number, so we want to give it a different name. There we go, 32 million, same number. I just wrote it down a little larger and without commas to give us some space to work. So what is this number? Well, this number is actually very similar to the totally modest number 3.2. All we have to do to 3.2 is take it and multiply it by 10 a whole bunch of times to get back to where we started. If we take 3.2 and multiply it by 10, we get 32. Multiply it by 10 again, 320, and so on. And every time we multiply by 10, we move the decimal place over one time. So how many times do we have to multiply 3.2 by 10 in order to get 32 million? Well, we have to do it 1, 2, 3, 4, 5, 6, 7 times. So our original number, our original 32 million, is exactly the same as 3.2 times 7 tens. Or, more scientifically written, that would be 3.2 times 10 to the 7th power. Let's put that in the right place. Now let's go the other way. Let's say we're looking at 4.56 times 10 to the 6th, and we want to be sure that we could write that as a, as it were, normal number. So what is that? That's the number 4.56, and then we have to multiply it by 6 tens. Each time we multiply it by 10, decimal place moves over, 1, 2, 3, 4, 5, 6 tens. And I'm going to have to fill in each one of these gaps here with a 0, so in the end, I am going to get the number 4,560,000. Okay, let's spend a moment talking about proper scientific notation. This first number here, 5.23 times 10 to the 8th, that's in what we'll call proper form. What we mean by that is it starts out with a single digit. That's a digit between 1 and 9 before the decimal place. And that's what you have to be in proper scientific notation. The second number here, 76.4 times 10 to the 21st, that's not in proper scientific notation because that 76 is 2 digits instead of 1. There's going to be good reasons for this. We'll see soon. So let's take that second number and try to write it in proper scientific notation. So this number, 76.4, is not in proper scientific notation because it has those 2 digits before the decimal place and it's only allowed to have 1. We want to write it in proper scientific notation. What's that going to look like? Well, this first number here is going to be the same as 7.64 times, well, not times a single 10, times some number of tens. And we want to say, how many tens do we need? Well, let's think about this bit. What is 76.4? 76.4, it's a number. Well, another way to write it will be 7.64 times 10. Two numbers, the same thing. So if we want to turn 76.4 into 7.64, we're going to have to do it by taking a 10 out of the 76.4 and adding it to these 21 tens. So we're going to get the original 21 tens and one more. And what we're going to end up with is going to be 77.64, I say that correctly, times not 21 tens, but rather 22 tens. Sometimes we have to go the other way. Let's say we're looking at this annoying thing, 0.052 times 10 to the 12th. And again, we want to write it in proper scientific notation. It isn't because you've got a 0 before the decimal place. And in proper scientific notation, you have to start with a single digit that's between 1 and 9. So in proper scientific notation, this would turn into 5.2 times 10 to some power. Again, what is that power going to be? Well, we want to take our 0.052 and see what we have to do to it to kind of turn it into a 5.2. Let's think about that. 5.2 is what you get by taking 0.052 And multiplying up by 10 once, that would give you 0.52. And then by 10 again to get 5.2. So we're going to have to steal 2 tens away from this pile over here to turn 0.052 into 5.2. In other words, our final answer is going to be 5.2 times 10 to 2. I have 2 fewer tens. I'm going to get 5.2 times 10 to the 10th. And now these two numbers are exactly the same as one another.